to the notes for AP Calculus on the topic of advanced area problems continued. So on this one it says let S be the region in the first quadrant, bounded above by the graph of the polar curve r equals cosine theta, and bounded below by the graph of the polar curve r equals 3 theta. Okay, so here's our region S here. This dotted line here is not r equals 3 theta. That would be a linear equation, and polar ones, remember r is a constant, but see here r is not a constant. It's not just 3 times theta. So it's not that one. So based on the description of this, you can tell above it's talking about this graph right here. This is the above one. This is r equals cosine theta. And below, it's talking about this one right here. We'll see why that dotted line is there, that they put in there to help you set it up correctly. So this one is r equals 3 theta. We can see that on our calculator. We put those in here. So on this one, you can go math. Oh, sorry. Put in polar mode first. So go mode, polar for polar, and then y equals r1. You can type in cosine theta, r2, 3 theta, and then window size. We're just looking at the first quadrant, so you can make, we'll deal with the thetas here in just a second. X minimum -1. Let's say to 5, and y minimum -1 to 5. So we're just focusing on the first quadrant there. We can still see the axes. And the theta min and max here, you could go 0 to 2 pi, but remember I just said just in the first quadrant. And if you look at each of these equations, in the first quadrant cosine is never negative, so it's not going to give you any negative rates. And if you plug in something between 0 and pi over 2, and in this equation, it's not going to give you any negative either. So it's just going to be the standard, most common angles you get when you don't have negative values for r, that the most common is 0 to pi over 2. So put in 0 as our theta minimum, and pi over 2 since we're just focusing on the first quadrant. And then we can graph. Okay. So you can see this was the graph of the cosine there. And then this one is the graph of 3 theta. So if you want to zoom on a little more, you don't have to. You could change it -1 to 2 on each of these. Just so you can zoom in on a little more to see what region it's talking about. Yeah, so here's the cosine graph. You can see it starts at angle 0 at 1, and then over here by pi over 2 at 0. And here you can see 3 theta, just a little close to the axis. You can't see, kind of like right here. Where notice as the angle gets bigger, r gets bigger and bigger and bigger as we go. And so this is where they intersect. So we're trying to find this area. And let's put these on the Inspire real quick. So new document, add graphs. Again, if you want to see in the polar form, you can entry edit, change to polar. And then R1 was cosine of theta. Again, theta is right here on the pi button. And then can change our theta min and max to, again, since it's just in the first quadrant, 0 to pi over 2. Okay, so there it is. And then tab R2, again, was 3 theta. And again, just graph it from 0 to pi over 2. In the first quadrant here. Okay. So again, if you want to zoom in on it, window settings, you can make it -1 to 2 again on the x min and max and y min and max. But you don't have to do that. This is just to help you kind of visually see what it's giving you, because they already gave you the graph here. Okay. So we're talking about this region right in here. So let's see how we're going to set this one up here. Well, notice what's going to happen here is, remember we're using these little kind of tiny slices of a circle with different radii. So for this part, all these angles starting with 0, you can see it's between this curve and the origin. So this is our radius here. And that's true, it's between this curve until we get to this point right here. Then it changes to be between this curve and the origin. Notice, this is not one where you need R1 and R2 because you're not looking for the area between these two in terms of how far they are from the origin. That's when you'd need, if one was over here and there's R1 and here's R2, then you would need that, but not in this case. So it's a little bit different in the setup. What we have to do is realize, well, we use this curve's R until we get to this point, and then we use this curve's R from this point on to pi over 2. Because it's like we're starting at theta equals 0 right here, and then going all the way to theta equals pi over 2 in the first quadrant. So we have to find where they intersect. And again, as far as I know, I don't think the graphing calculators allow you to do this in polar format. So, second quit on 84, mode, just go back to regular function mode. And then y equals. And we'll just clear these out here. Again, basically what we're trying to do is set these equal to each other. So, since they're both r equals, you can think of it just substituting 3 theta in for r right there. So we're really trying to see where does 3 theta equal cosine theta. And again, because one theta is inside cosine and one is not, this would be kind of tough to solve by hand. So our calculator can enter in one of these as 3x. We'll just use x instead of theta, and the other is cosine x. Or you could also use r1 of x and r2 of x, since we've already entered in as our calculator, either way. Going to vars, y variables, and polar. Oops. Vars, y variables. If you go to number 3, polar, you'll see them listed there. You do r1 of x for y1 and r2 parentheses of x for y2, either way. And then window size, we just want to look where they intersect between theta equals 0 and theta equals pi over 2 in our first quadrant. So it'd be 0 to pi over 2. See where they intersect. And then y min and max, let's just make that, since these are not negative ever, we don't have to work with the negative values, -1 to, let's say, 2 again, and graph these. So you can see on this interval there's one place where they intersect right there, so that's what we need to find. So second calc, number 5 intersect. First curve, y1 enter, second curve, y2 enter, and yes, you can move it over here, but really there's only one point of intersection on this interval, so you don't have to move it that close to it. And you get 0.317. So that's theta. If you round it. And we're going to need this in our calculation for the area, so let's store this in our calculator. I'll call it alpha A. So I'll just say this is equal to capital A there. So now when we set up our area, well actually let's do this on the Inspire first. Here you can go doc, insert graphs first. And again, here's the other way that you can go, R1 of x if you want, and R2 x. This is the other way you can also do on the 84. And you can see the point of intersection there. There's only one in this case, but sometimes there might be more than one, so you can change your window settings. We really are only looking between 0 and pi over 2 on our x min and max. And there it is. So menu, analyze graph intersection. Lower bound here, upper bound to the right of it, and there it is, same value. And store it as a. Alright, let's finish setting it up for the area now. So, remember the formula for these polar ones with area, you've got a 1/2 out in front. But what's different about this one, we're going to use this curve here below. That's going to give it area, those little wedges of circles, until we get to theta equals 0.317. So this one integral is going to be from 0 to a, and then we'll have this radius 3 theta squared d theta. That'll give us the area up until this dotted line here. All these little segments of circles up until there. And then plus, again, 1/2 out in front. This one is going to start at A and stop, since we're stopping just in the first quadrant, at pi over 2. And this time we're using this one, you can see this would be our R, how far it is from the origin at that point on. And that would be cosine of theta, and again the radius gets squared. So cosine theta squared d theta. So that's the setup that gives us the area of this entire region S. And now all I have to do is put this in our calculator on both of them. So back to the 84 here. So you can put 1/2 or 0.5. And then actually if you want to put it with thetas instead of x's, either way is fine. You can go to mode and switch it back to polar mode. So then you go math 9 function integrate, and you can either write it this way with parentheses 3 theta close parentheses squared, or you could actually square it out as 9 theta squared without the parentheses. Either way is fine. Comma, thetas are variable, comma lower limit 0, comma upper limit alpha a. And then close parentheses on the integral plus 0.5, and the other one math number 9. And here open parentheses cosine of theta. Close parentheses on the cosine, close parentheses so we can square cosine. Then comma, thetas are variable, comma lower limit alpha a, comma upper limit pi over 2. And we get 0.287. And if you notice, that was a pretty small region there, so let's see why we got such a small answer. Again, if you want, you can put units squared, but you don't have to since we are not given specific units. And then on the Inspire, again, you just go dock, insert calculator. And again, you can either use x or theta, it's up to you here. So again, I'll just go 0.5, integral from 0 to a, and then I can type in 3 theta, or you can also enter in a R, that was our R1. Theta squared. Or I could do 3 theta squared either way. And if we go back here, remember our R1. Oops, our R1 was cosine actually. So this would be R2. 2 theta squared d theta. And then plus 0.5 integral from a to pi over 2. And then r1 squared or cosine squared either way. And we get the same answer. Alright, so it's just a matter of having to split up, kind of like we did with rectangular coordinates, when it's not always between the same two curves. This one, if the origin is not, and the region is not always going to the same curve here. It goes to this lower curve until we get to theta equals 0.317, and then after that it goes to this other curve. So that's what requires this split. So they drew the dotted line here to show you exactly where you're splitting it. Alright, the next one says what's the total area between the polar curves r equals sine of 4 theta and r equals 7 sine of 4 theta. So, let's see what this looks like here. And in polar mode here, I'm going to clear these two out and enter these two in. So r1, 3 sine of 4 theta. Oops. And r2, 7 sine of 4 theta. And then on the window size, we don't necessarily know what's going to be the entire graph. Usually the most common thing is 0 to 2 pi, but occasionally it repeats more often than that depending on the equation. So if you want to be safe, just try 0 to pi to start with. And let's make our x minimum. You can see sine goes up to 1, so this one could go as large as 7. So let's go from negative 8 to 8 on the y minimum x. Whoops, that was a scale. Scale 1. X minimum, negative 8, x maximum 8, y minimum, negative 8, y maximum. And then graph these. So there's the graph of the first one, the second one there. And let's see if that's the complete graph. It looks like it could be. But if we change our window size now to 2 pi, let's see if it gives us any more or not. So you can see, yeah, that 0 to pi was not the complete graph here, 0 to 2 pi. So based on this, notice the first one was this little flower here, and then the second one was the big flower. So you can see from 0 to 2 pi, the area we want between the polar curves is these sections right in here. So this is where, but notice it's between, you have R1 that's from the origin to the smaller curve, the 3 sine 4 theta, and R2 is to the larger one. Then we're trying to find the area between those there. So we can set it up as 1/2. We just saw to get the entire graph we need to go from 0 to 2 pi. And our R1 was the one further away, which was this one. See, based on the 7, it was out there and graphed it second, so this would be 7 sine of 4 theta squared d theta. I'm sorry, not d theta. That's our R1, our outer radius. And then R2, inner radius is this one. So it'd be minus 3 sine of 4 theta squared, and then the whole thing times d theta would be this side there. Notice how it's different than the one we just did, but here it wasn't between the two, the origin, one wasn't separating one of them from the origin, they were both the different graphs together, and here it's actually between the two in relation to the origin. Okay, so let's do this on Inspire real quick. create a new document. Add graphs. You can see again, first one was 3 sine of 4 theta and 7 sine of 4 theta. So I'll put this in polar mode again. Menu, polar. 3 sine of 4 theta. And we did 0 to 2 pi, which is the default here. Gives you that one. And then 7 sine of 4 theta. So again, you can see R1 is out to here, is the one further out, and R2 is the one inside there. We're trying to find these areas between the two curves. Okay, so now it's left to just put these in our calculator. Let's start with the 84. So again, since we're in polar mode, you can just quit out of here and go 0.5 for the 1/2. Then math number 9, function integrate. And then we want this first one squared. So open parentheses. And that was my R2 in the calculator, even though R1 in terms of being the outer radius. Polar. R2 squared. So because R2 is already in there, I don't have to put this parentheses. Delete that. So R2 squared minus R1 squared. Comma, thetas are variable, comma, lower limit 0, comma, upper limit 2 pi. And we get 62.832. Again, it's area, so you could write it in square, but you don't have to. And let's see if we put the same thing on the aspire here. So doc, insert, calculator, and 0.5, interval from 0 to 2 pi. This one we do need open parentheses. That's R2, one that was further away. Actually R1 in terms of the graph, but R2 in terms of how we typed it in. Theta squared. And nice thing when you put minus here, it automatically puts these outer parentheses for you. That's going to be times the d theta. R1 theta. Oops, I forgot the parentheses here at the beginning. Put parentheses on that. Squared and d theta. I get the same answer. All right, let's take a look at one more. This one's a little different. It says the figure above shows the graph of the polar curve, and I apologize, there's a little typo on here. I think on yours it might say 3 minus 5 cosine theta, but it doesn't quite match this graph if it says that. So just change this to be 2 minus 4 cosine theta from 0 to pi, and the circle r equals 2. So you can see here's our circle. When the radius is a constant like that, it just creates a circle, in this case a radius of 2. And we want to find the area of the shaded region. So, there's different ways to think about it. So you can think of the whole circle minus this. But notice here, we just have a quarter circle right here. Really, we just want to take the quarter circle, the 3/4 of the circle, minus these regions right here, right? So basically the idea, we're going to take 3/4 to the circle, and then subtract these here, these little slices here we need to find here. So let's start with the easy part of this, the 3/4 of a circle. So it'd be 3/4, and we can see the circle has a radius of 2, so 3/4 pi 2 squared, the area of the circle, minus, well, to get this area, that's the part that's tricky. Notice, it's kind of like those problems where it's in certain quadrants we're looking for. In this case, we're trying to find where does this, because this is between this curve here, which they give you, 2 minus 4 cosine theta, and in the third quadrant, and then here in the first quadrant as well. So you need to figure out where are those here. So it gives you a clue because it's going from 0 to pi. Right? So let's start by substituting some easy angles in there and see which points they give us. Because either this is the starting point here or this is the starting point here. So let's try substituting in r equals 0. So if r equals 0, you get 2 minus 4 cosine of 0. But cosine of 0 is just 1. So this would be 2 minus 4 times 1 gives you 2 minus 4, which is negative 2. So 0 is this direction, but we have a negative value for the radius, so it goes negative 2. And notice we know it's going to be right here because this circle has a radius of 2. So this corresponds to theta equals 0. So it looks like that's where we're going to start here instead of here. If we'd gotten a big number larger than 2, like 4, negative 5, in terms of being negative in size larger, then we would know we'd be starting at this part of the curve. Let's try the next easy one. Let's say we try pi over 2. So just say r equals. And then r equals pi over 2 would be 2 minus 4 cosine of pi over 2. But cosine of pi over 2, right here, is 0. The x coordinate there. So this would be 2 minus 4 times 0, just 2 minus 0, which gives you 2. So pi over 2 is this direction, straight up from the origin, and 2 takes you again right here, because we know it's on the circle. So in this case, to get these two regions, notice it starts at 0, that gives you up until here. We could find what this is, but it's the same curve, so we don't need to split it up, and go all the way to pi over 2. So to get that area of that region, it'd be 1/2. Now we know where that next part of the curve starts and stops, from 0 to pi over 2. And then we have our radius right here, so the 2 minus 4 cosine theta squared times d theta. That'll give us the area of those two regions in green there. And then you can put this in our calculator. Notice you could simplify this one if you want. The 2 squared 4 and this 4 cancel out, so this just ends up being 3 pi. Makes it a little simpler to type in your calculator. And since they already gave us the graph, this is the only part we really need the calculator for. So let's start with the 84 here. So you go 3 pi minus 0.5, math number 9, and then open parentheses, 2 minus 4 cosine. I have it in polar mode, so it's theta, but if you have regular mode, you could use x as well. Close parentheses there, squared, comma, thetas are variable, comma, lower limit 0, comma, upper limit pi over 2. And we get 8. So it works out to be an integer here. And you can see if that seems reasonable here. You can unit squared if you want to. So notice our quarter circle was 3 pi. which is a little more than 9, and we're subtracting these. So that seems pretty reasonable that it's about 8, based on what we started with and what we subtracted. Now, so we have the same thing on the inspire here. So 3 pi minus 0.5, interval from 0 to pi over 2. Parentheses, 2 minus 4 cosine, again you can use x or theta, just be consistent, whichever you use, and that gets squared times d theta. And we get 8 that way too. And that concludes the notes for AP Calculus on the topic of polar equations, advanced area problems. Continue.